To look out into the deep, quiet expanses of the night sky is to gaze upon a grand illusion, a shimmering veil of light that hides the true, silent architecture of the cosmos. For what we see, the scattered diamonds of stars, the swirling arms of galaxies, the hot, glowing gas, is merely the foam atop a vast, invisible ocean that stretches through the darkness. We are accustomed to believing that light is the truest messenger of reality, that what glows and shines is what exists. Yet the story of our universe is not written in light, but in the heavy, silent hand of gravity. The primary author of this cosmic history is a ghost, a presence we have never seen, never touched, and never captured, yet without which the very structure of our existence would crumble into dust. This is the story of dark matter, the unseen scaffolding that holds the stars in their orbits, and the slow drift of this mysterious substance as it weaves the great cosmic web, a structure so immense that it defies human comprehension, linking galaxies across billions of light years in a tenuous, invisible lattice. To understand this drift, we must first unlearn the bias of our eyes, which are tuned only to the narrow frequencies of the electromagnetic spectrum, and instead learn to see with the mind, using the language of gravity to map the contours of the dark. Imagine, if you will, that you are floating in the intergalactic void, far from the warmth of any sun, in the deepest, coldest stretches of space between the great clusters of galaxies. Here, the silence is absolute, and the darkness is total, save for the faint, distant smear of island universes, appearing as mere smudges against the velvet black. In this apparent nothingness, you are actually suspended in the thickest part of the universe's skeleton, surrounded by a substance that passes through you as if you were made of mist, a substance that does not interact with light, does not reflect, absorb, or emit any radiation we can detect. Yet it possesses mass, and therefore it possesses gravity. It is here, in the quiet dark, that the universe's true mass resides, flowing in slow, cold rivers that guide the visible matter, the hydrogen, the helium, the dust, into the pools and eddies where stars will eventually ignite. This is the realm of the dark sector, a domain that constitutes roughly 85% of all the matter in the universe, leaving the normal baryonic matter, the stuff of atoms, of us, of the earth, as a mere minority, a dusting of snow on a vast, dark mountain range. The realization that our universe is dominated by this invisible giant did not come as a sudden epiphany, but rather as a slow, creeping unease, a mathematical whisper suggesting that something was wrong with our accounting of the cosmos. It began in the early 20th century, a time when astronomers were just beginning to understand that the Milky Way was not the entirety of the universe, but merely one of countless galaxies drifting through space. In the 1930s, the Swiss astronomer Fritz Zwicky turned his attention to the Coma Cluster, a massive aggregation of over 1,000 galaxies located some 320 million light-years from Earth. Zwicky was a man of sharp intellect and often abrasive personality, but his vision was clear. He sought to weigh the cluster, to determine the mass required to bind these hundreds of galaxies together in their gravitational dance. He measured the light coming from the galaxies, estimating their mass based on the number of stars they contained, a standard practice of the time that assumed that mass and light were inextricably linked. But when he measured the speed at which these galaxies were moving, zipping through the cluster at velocities that seemed defyingly fast, he encountered a paradox that would haunt astronomy for decades. The galaxies were moving so rapidly that the visible mass of the cluster, the stars and gas he could see, was nowhere near sufficient to hold them back. By all rights, the Coma Cluster should have flown apart billions of years ago, its member galaxies flinging themselves out into the void like stones from a spinning sling. Zwicky realized that for the cluster to remain stable, for gravity to keep a tight grip on these racing galaxies, there had to be more mass, much more mass, hidden within the space between them. He calculated that the cluster required hundreds of times more matter than what was visible to account for the observed velocities. In a stroke of intuition that was decades ahead of its time, he dubbed this missing mass Dunkel Materie, or dark matter. It was a radical suggestion, implying that the universe was filled with invisible material that betrayed its presence only through the force of its gravity. For years, Zwicky's observations remained a curiosity, a jagged edge in the smooth puzzle of cosmology, largely ignored as observational errors or misunderstood physics. The scientific community was not yet ready to accept that the majority of the universe was hiding in plain sight, or rather, hiding in plain darkness. The whisper of dark matter grew into a clamor in the 1970s through the meticulous and transformative work of Vera Rubin and Kent Ford at the Carnegie Institution of Washington. Rubin was interested in the rotation of spiral galaxies, the beautiful, pinwheeling structures like our own Andromeda or the Milky Way. According to the laws of Newtonian physics, and indeed the laws that govern our own solar system, the speed of objects orbiting a massive center should decrease as they get further away from that center. Mercury whips around the sun at a frantic pace, while distant Neptune lumbers slowly along its orbital path. The expectation was that galaxies would behave similarly. The dense concentration of stars in the galactic bulge would dictate the gravitational pull, and the stars in the sparse, outer spiral arms would move slower, trailing off into the quiet of intergalactic space. Rubin pointed her spectrograph at the Andromeda galaxy, measuring the Doppler shift of the stars to determine their rotational velocity. And what she found was a stunning contradiction to the established order. The stars at the very edge of the galaxy were moving just as fast as the stars near the center. The rotation curve did not drop off. It remained flat, extending far out into the dark halo surrounding the visible disk. If the visible stars and gas were the only source of gravity, these outer stars should have flown off into the cosmos, unbound by the galaxy's grip. The fact that they remained tethered, racing at high speeds in stable orbits, implied that the galaxy was embedded in a massive, invisible sphere of matter, a dark halo that extended far beyond the luminous arms. This halo provided the extra gravitational glue needed to hold the high-speed stars in place. Rubin observed this phenomenon in galaxy after galaxy, a systematic anomaly that could not be explained away. The conclusion was inescapable. Galaxies are not merely islands of stars. They are peaks of visible light floating in vast, unseen clouds of dark matter. The visible galaxy is just the tip of the iceberg, the glowing beacon at the center of a much larger, darker structure. This revelation fundamentally shifted our understanding of the cosmos, forcing us to reimagine the universe not as a collection of glowing objects, but as a vast, interconnected web of dark matter, with the visible universe merely tracing the densest knots of this web. We began to understand that dark matter is not just a static filler. It is the architect of the universe. In the earliest moments after the Big Bang, the universe was a hot, dense soup of particles, expanding rapidly. As it expanded, it cooled, and tiny fluctuations in the density of the dark matter began to grow under the influence of gravity. Dark matter, being immune to the pressure of radiation that pushed ordinary matter apart, began to collapse first, pooling into clumps and filaments, creating gravitational wells. These wells acted as seeds. Ordinary matter, hydrogen and helium gas, was drawn into these dark matter wells, falling into the gravitational embrace of the invisible. As the gas accumulated, it compressed and heated up, eventually igniting to form the first stars and galaxies. Thus, every galaxy we see today, every star that twinkles in the night sky, owes its existence to a womb of dark matter that gathered the gas together in the deep past. This structure, this primordial framework, has evolved over 13.8 billion years into what we now call the cosmic web. It is a structure of incomprehensible scale, consisting of vast, thread-like filaments of dark matter that stretch for hundreds of millions of light years, crossing the abyssal voids of the universe. These filaments are the highways of the cosmos. Along them, gas and dark matter flow, drifting slowly toward the massive intersections where the filaments cross. At these intersections, the density is highest. These are the nodes of the web, the locations of the great galaxy clusters like Coma and Virgo. The voids between the filaments are immense regions of emptiness, spanning hundreds of millions of light years, from which matter is slowly draining away, falling toward the filaments and clusters. The universe is therefore not a uniform scattering of galaxies, but a foam-like structure, a cellular network where the walls are made of dark matter and galaxies, and the interiors are empty bubbles of repulsive nothingness. To visualize this, one must imagine the universe as a three-dimensional spiderweb, but one where the silk is invisible and sticky with gravity. We only see the dewdrops caught on the silk, the galaxies, shining in the morning light. We trace the lines of the web by connecting the dots of the galaxies, but the web itself remains hidden. Yet, modern astronomy has given us tools to see this invisible structure through the phenomenon of gravitational lensing. Einstein's general theory of relativity taught us that mass warps the fabric of space-time, creating curves and valleys along which light must travel. When light from a distant galaxy passes through a massive concentration of dark matter, say, a cluster, or a thick filament, its path is bent, just as light is bent by a glass lens. This bending distorts the image of the background galaxy, stretching it into arcs or creating multiple images. By carefully analyzing these distortions, astronomers can map the distribution of the mass that caused them. They can reconstruct the topography of the dark matter, creating maps of invisible mountains and valleys, revealing the clumpy, filamentous nature of the dark sector. These maps reveal a universe that is dynamic and slow-moving. Dark matter is not static, it drifts. It is cold in the terminology of cosmology, meaning that its particles move slowly compared to the speed of light, allowing them to clump together under gravity rather than streaming apart. This cold dark matter, CDM, paradigm explains the structure of the universe with remarkable accuracy. Simulations run on the world's most powerful supercomputers, simulations like the Millennium Run or the Illustris project, start with the conditions of the early universe and let the laws of gravity and dark matter physics play out over billions of simulated years. The result is a virtual universe that looks startlingly like the real one. A complex network of filaments, voids, and clusters, a precise match to the large-scale structure we observe in the sky. These simulations show us the slow breathing of the cosmic web, the gradual gravitational collapse that pulls matter from the voids into the filaments, and from the filaments into the clusters, a cosmic flow that has continued for eons. However, the nature of the dark matter particle itself remains one of the deepest mysteries in science. We know what it is not. It is not protons, neutrons, or electrons. It is not black holes, at least not primordial ones in sufficient numbers. It is not neutrinos, which travel too fast to form the clumpy structures we see. The leading candidates are hypothetical particles, like weakly interacting massive particles, WIMPs, or actions, ghostly entities that pass through the Earth and our bodies by the trillions every second, leaving no trace. They interact with our world only through gravity, and perhaps, very rarely, through the weak nuclear force. Deep underground, in mines shielded from cosmic rays, detectors filled with liquid xenon or germanium crystals wait in silence for the faintest nudge of a dark matter particle colliding with an atomic nucleus, a subtle signal that would confirm the existence of this shadow world. But so far, the detectors remain quiet, hearing only the background hum of the universe, leaving us with the macroscopic evidence of the skies, the rotation of galaxies, the lensing of light, the motion of clusters as our only proof. The drift of dark matter is the drift of history itself. It is the slow accumulation of structure in a universe that began as a nearly smooth sea of energy. As we trace the filaments of the cosmic web, we are tracing the lineage of gravity, following the invisible rivers that fed the first galaxies, the tension between the expansion of the universe, driven by the even more mysterious dark energy, and the cohesive pull of dark matter defines the fate of all structure. While dark energy tries to tear the universe apart, stretching the voids and pushing galaxies away from each other, dark matter tries to hold it together, binding the clusters and filaments in a desperate gravitational grip. It is a slow, cosmic tug-of-war played out over billions of years. And for now, the webs of dark matter still hold firm, guiding the slow drift of galaxies through the endless night. As we descend deeper into this narrative, we must prepare to examine the specific mechanics of this web. How does a filament form? What happens when two massive halos of dark matter collide? How does the temperature of dark matter affect the birth of dwarf galaxies? We will journey into the simulation data, visualizing the purple and blue tendrils of the dark web as they span the parsecs. And we will look at the bullet cluster, the smoking gun of dark matter's existence, where the separation of visible gas and invisible mass was caught in a violent celestial crash. We are embarking on a voyage through the unseen, guided only by the warping of light and the whisper of gravity, into the heart of the cold